is graph theory. So we will start off with a very famous problem called the 7 Bridges of Königsberg. Königsberg is an old city. It used to be located in Prussia, but that's no longer a thing.
What's Prussia?
Prussia is an ancient, or not that ancient, but it's an old nation that used to exist in this area, but it eventually became Germany. Yeah, we're not here to learn about history though. But basically just know that it's now known as Kaliningrad. Some nice, interesting pieces of trivia, and it's now part of Russia. But yeah, does anyone know of this problem? Does anyone know anything of this problem and want to share with the class? Remember, use the raise hand function on Zoom. If you don't know anything of it, that's okay too. I don't expect you to. That's totally fine.
Königsberg?
Yeah.
Wait, were there actually 7 bridges?
There were actually 7 bridges. Yes, that is the origin of this problem. Yeah, all right. So that's okay. So this problem, yeah, basically this is an actual place. It used to be an actual, like these bridges actually existed. Königsberg, which was an actual city. I believe 2 of these bridges have burned down now, but back in the day, there were these 7 bridges that connected these 2 islands to these 2 banks of this river. And basically what this question was asking was, is it possible to use each of these bridges exactly once and also end up where you started? So basically the motivation for this was probably people just going on their walks in the evening or something, wanting to see all of these bridges, just wondering, is it possible to use each of these bridges exactly once and also end up where you started? And this problem is the birth of graph theory, and we will talk a little bit about why and how graph theory kind of originated from that.
Well, in a math class, I did this problem, and then my entire class was just messing around for an hour trying to figure it out. But then the teacher went in and said, "There's no solution," and all of us were just betrayed, I suppose.
Oh, well, we
so
will learn. Yeah, that's okay. So it is quite fun messing around along with these graphs, trying to see if certain solutions exist. Yeah, and we will learn about the solution to this problem throughout this class, and yeah, understand how we got to that solution as well. All right, so first, what are graphs? We are going to be talking about graph theory today. We should probably learn what a graph is. A graph is basically a set of vertices or points or nodes and edges. So vertices are like a point like this, and an edge is a connection between 2 vertices, usually drawn like this. So that is an edge between 2 vertices. And graphs are a connection, are a collection of vertices and edges that basically show the relationships and the connections between those. And that is the vital thing that they show. You don't really care about like the angles between these edges or anything like that, like you might in geometry. You just care about which vertices are connected to which edges, how many times they're connected, etc. All right, so now that we've learned about what a graph is, let's try to represent this problem as a graph. There was this really smart guy called Euler back in the day who solved this problem eventually. And what he realized is that you don't really care about the specific shapes of the islands or the exact spatial location of them. You just care about how they're connected to each other. And that can be represented in a graph. And that's actually why this problem was kind of the origin of graph theory. So if we have these 4 kind of land masses and these 7 bridges, if we're drawing this problem as a graph, does anyone want to tell me how many vertices and edges do you think this graph would have?
Wait, what was the problem for the Königsberg? Like, what were we trying to solve?
We're basically asking, is it possible to use each of these bridges exactly once and also end up where you started?
Would you just use a boat?
Well, you want to see the bridges, and that is the point of this problem. So, yeah, you want to use the bridges.
Or an airplane?
You could use a boat and get to where you want to be, but we are thinking about whether it's possible to cross these bridges like that. All right.
Oh, if walking?
Someone guessed 7 vertices. Not quite. 30 vertices. Not quite either. That's okay. So basically, we can think about what are the things that we want to be connected and what are the things that we are using to connect them, because the vertices are basically the things that are being connected in a graph, and the edges are the connections. The edges represent the connections. So in this case, we have 4 kind of objects that we're trying to connect. We have these 4 land masses, A, B, C, D. So in this case, we are going to have 4 vertices, A, B, C, and D, because those are the 4 kind of objects. You can think of them as that we are trying to show the connections between. We don't really care about the connections between the bridges because there are no connections between the bridges. They're not really relevant to us. We are just thinking about how we can connect these land masses. And in our graph, we are also going to need connections between these 4 land masses, and that's what the bridges are going to represent. So the bridges are going to kind of represent our edges here, and that's why we're going to have 7 edges, because we have 7 bridges, which are our connections. Can you explain the vertices thing again? Yeah, so you can kind of think of the vertices as like the things you're trying to connect. So another common application of graph theory is like social networks. So in social networks, you could have each person be representing a vertex, and then you can show connections by drawing edges between those people. And it's like those people are the vertices because they are the objects that you're trying to connect. And then the edges in your graph represent which of these people are connected. Does that make sense? Okay, awesome. All right, so now that we have our 4 vertices and that we've determined our number of edges is going to be 7, let's try drawing the relationships between these. So let's not all go all at once. Someone raise their hand to volunteer to annotate on the screen and show what the graph will look like and draw the edges for us. All right, Grace, go ahead.
Sorry about the cutout lines. My mouse is having problems.
Nope, no problem. This is looking great so far.
And that's all.
All right, that's awesome. That is exactly right. So Yeah, so we see here we have A with 2 connections to C. Exactly. We see bridges 7 and 4 are the 2 connections between A and C. It does matter that there are 2 connections. The number of connections also matters. And we also see there is a connection between C and B. There's an edge there, which is going to be represented by bridge 3 right over here. You can see there's a connection, a direct connection between C and B. There is also a direct connection between B and D, which is bridge 1. And there's also a connection between A and B, as well as 2 connections between A and D. So, awesome job. Yep, that is what we would use to represent this problem. This is the 7 bridges of Konigsberg graph. And if we count up the edges here, we note that there are indeed 7 edges. There's one right here, another one here. What's 1, 2, 3, 4, 5, 6, and 7. So those are our 7 bridges connecting these 4 land masses. Awesome. All right, so the thing about graphs, they're kind of different from like polygons and shapes like you might have learned about in geometry class. They're only really here to show connections between vertices, not really the specific shapes of the edges or anything like that. So looking at these 2 graphs, do you think these are showing the same relationships? Are they equivalent? So to the person that said yes and no, mostly no. Okay. So we see a couple different answers in chat. We see a couple people saying yes. A lot of people saying yes. All right, a lot of people, it seems we have reached a common consensus of yes, they are equivalent. So can someone raise their hand, and someone that said yes, raise their hand and explain to us why these 2 graphs are equivalent, because they are equivalent. Rose?
So the bottom one, the C has 1 connection to B and 2 connections to A. On top picture, it has 2 connections to A and 1 to B. And then for B on the bottom picture, it has 1 connection to C, 1 connection to D, and 1 connection to A. On the top picture, it also has the same thing. So on the bottom picture D, it has 2 connections to A and 1 to B. The D over here has 1 connection to B, and the one that's over here is the one on top, sorry. And it has 1 connection to A on the bottom and 1 connection to A on top. So then the A has 2 connections to B on the bottom, 1 connection to B, and it has 2 connections to D and 2 connections to C. On top, it has 1 connection to B, 2 connections to C, and 2 connections to D.
Yeah, exactly. Yeah, I love how you explained that in terms of connections, and that is exactly why they are equivalent. They show the same relationships between these vertices because they show the same connections, even though it's rearranged a little spatially, so it looks a little wonky. They have the same edges, showing the same relationships between the vertices, so they are going to be equivalent. All right, what about these 2 graphs? Do we think these 2 graphs are equivalent? All right, see a couple people saying no in chat. Several people saying no. All right, seems we have reached a consensus that, yeah, it's the imposter. Yeah. Yeah, so the answer is indeed no, they are not equivalent. Ooh, we have someone typing in chat. in the first graph, A has 2 connections to B, but in second graph, it only has 1. Yes, so that is an excellent way of kind of spotting the difference between these two graphs. Yeah, they are showing different relationships between these kind of vertices. If we label them like this, they will be flipped. Yeah, that's exactly what I did. Yeah, I flipped B and C. All right. So just some terminology I'm going to introduce to you guys that will be used later. There are some things in graphs that are less common. Some include multiple edges and loops. So these kind of two features of some graphs basically mean it is what it sounds like. There's multiple edges connecting two vertices. So this image right here would be an example of that. There's two edges connecting the vertices V1 and V2. There's also some things called loops where you basically have an edge connected to itself. You can see why we call it a loop, because when we draw it, it looks like a loop. And so there's also something called a simple graph, which is basically a graph that does not have multiple edges and does not have loops. And yeah, we just introduced that concept because most of the time we're going to work in simple graphs because they are nicer and oftentimes more representative of real world situations. So simple graphs don't have the two things above it. I'm not sure what you mean by the two things. If you could expand that, I might be able to help. Yep, they do not have loops and multiple edges. Yep, that's right. Simple graphs do not have loops and they do not have multiple edges. Someone asked in chat, how do you make simple graphs? Just make a graph, any sort of collection of vertices and edges that do not have either of those features, and then you will have a simple graph. That is the kind of criteria for that. Another concept in graph theory is a walk. You can basically think of it as like exactly what it sounds like you're walking along this graph. It's a sequence of vertices and edges that allow you to kind of travel around this graph, starting at a vertex, using a specific edge to go to another vertex, using another specific edge to go to another vertex, etc., 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 ending at whatever vertex you decide to end at. So you have more than two vertices. Not sure what you mean by that, if you could attach it to a different question. All right, so another important concept is the degree of a vertex. And the degree of a vertex is the number of edges that contain that vertex. And yeah, that will come into play later. And another thing about degree is that if you have a loop, then it counts as like 2 for that vertex because it kind of comes out and then it goes back in. So we count it as 2 for the degree of that vertex. No, you do not need more than 2 vertices. If you have a vertex like this and like this, that's technically a simple graph. It's just not very useful, I guess. I mean, it could be useful, but yeah, that would be a simple graph, yeah. So it does not have multiple edges, and it does not have a loop. All right, so now that we've learned what a simple graph is, do we think the 7 bridges of Königsberg graph is a simple graph? All right, someone in chat said no. Some more people saying no. Wow, a lot of people saying no. All right, and why is that? Why is it not a simple graph? Yeah, I see a couple of people typing in chat about the multiple edges. Yeah. So, yeah, the reasoning for this is that there are multiple edges, an example of multiple edges in this graph, because we have, let's just look at this vertex and this vertex right here. There is one edge connecting them, and there are two edges connecting them.
Wait, so is it a simple graph?
It is not. It is not a simple graph.
Because it's complicated?
Not because it's complicated. You can have not really that complicated graphs that are not simple graphs. Yeah, don't think of simple as in like not complicated. Simple is a specific kind of definition that we've created for certain graphs. Yeah, basically not containing loops, not containing multiple edges. Yeah, and so looking at this graph, we see that these two vertices have two edges connecting in between them, so that makes it non-simple. There are not actually any loops in this graph, so be careful. Loops is not loop is not like, oh, I can loop around this graph and come back. That's not a loop. A loop is when you have a vertex that is connected to itself like that, and we do not see that. So this graph, even though it does not have loops, it does have multiple edges, so it is not a simple graph. Königsberg reminds me of the city Königsberg. Yeah, Königsberg used to be a city. Yeah, that's what this problem is named after. So, all right. We also introduced the concept of degree, so let's just do a little practice with that. So let's find the degree of each vertex. Oops, this should be a K. Apparently, I do not know why I just said G for some reason. Bridges of Königsberg graph. But yeah, let's find the degree of each vertex in this graph, which is the 7 bridges of Königsberg graph. So I see. Yeah. Some people saying the degree of B is 3. That's correct. Degree of C is 3. That's also correct. Degree of A is 5. That is correct. The degree of 3 is 3. Yes. Nice. So yeah, that is the degree of each point. Yep. So in order to find the degree, basically look at the number of edges that contain that vertex. So for B, there are 3 edges that contain B, one right here, one right here, one right here. So that is a degree of 3 for B. That's an odd degree. And for D, we have 1, 2, 3 edges right there. So that is another degree of 3. For A is connected to a ton of things. A is connected to 1, 2, 3, 4, 5. Has 5 edges containing it, so that is a degree of 5. For C, we have 1, 2, 3 edges, so that is a degree of 3. Awesome. A is the only one that doesn't have 3 degrees. That is true. That is true. Good observation. Yep. Degree is exactly, that's degree is the number of edges that contain a certain point. Yep. Nice job. All right, so just a little bit more terminology. Connected is actually not super important for our class today, but a connected graph basically means that in this graph, there exists a walk from any vertex to any other vertex in the graph. It's exactly kind of what you think of. It's connected. You can go from any point in the graph, go along an edge, and go to any other vertex. So like an example of a connected graph, our 7 bridges of Königsberg graph is a connected graph, but a graph that maybe looks like if I did this, and then I did this, and this whole thing was my graph, that would not be a connected graph because I cannot go from this point right here to any of those points because there's no graph, there's no edges connecting them. Oops, I kind of answered that question for us, but yes, the 7 bridges of Königsberg graph is connected because there exists a walk from any point in that graph to any other point in that graph.
But is it possible to walk all the bridges?
Well, we'll be answering that question. Yeah, we'll see. You'll see the answer to that in just a little bit. A couple more terms to learn before we go on. Are Eulerian walks and Eulerian circuits. So an Eulerian walk is a path or a walk. This should really say walk. A walk that uses each edge exactly once. And an Eulerian circuit is an Eulerian walk that starts and ends at the same point. And that's why it's called a circuit, because it's kind of like you're going in a circuit. You start at one point and you go, use each edge exactly once and end back right there at that same point. It's like a circuit, a closed loop. All right. So going back to our original problem, what is the 7 bridges of Königsberg problem asking in terms of Eulerian walks and Eulerian circuits? Someone asked in chat, is a single vertex a graph? Yes. Yes, it is. Someone else asked our assignment. Oh, yes, that actually kind of answers our question here. Do you want to unmute and say something about it? Yeah, that's a great option. Yep, the 7 bridges of Königsberg problem is asking for an Eulerian circuit. Someone typed in chat. Yes, that is exactly what we're looking for. It is asking, does an Eulerian circuit exist for this particular graph? Our particular graph, our 7 bridges of Königsberg graph, like this. Yeah, it's asking, does an Eulerian circuit exist for this graph? Because remember, our conditions for that problem was, does there exist a walk such that you can start and end at the same place, which is the circuit part of the Eulerian circuit, and you can only use each bridge exactly once, which is the Eulerian part of that. So together, we are looking for an Eulerian circuit. All right, so basically what Euler said, what he observed or what he claimed and eventually proved, is that a graph, connected graph with an Eulerian circuit must have even degree for every vertex. So, does someone want to remind us what degree is? Rose?
A degree is the amount of like lines that one point is connected to any other point. So like A on the 7BOK graph, A has 5 degrees because it's connected to A twice, D twice, and B once. So 1 plus 2 plus 2 equals 5, so it has 5 degrees.
Yeah, so the degree of A there is 5. Yep, it's how many edges contain that vertex. Very good. Yeah, what having even degree means is basically the degree is even. It's an even number. So it could be 2, 4, 6, etc. You know what an even number is. Yeah. So what does this tell us about the answer to the 7 bridges of Königsberg problem? Yes, 3 and 5 are not even. That is true. So do we think the answer to the 7 bridges of Königsberg problem is yes or no? Yeah, the 7 bridges of Königsberg does not have an Eulerian circuit. Yeah, the answer is no to that problem because not every vertex has even degree in that graph. In fact, none of them have even degree in that graph. So there does not exist an Eulerian circuit. It is not possible to traverse those bridges, all of them exactly once, and end up in the same spot. Why do we think this is true? Why do we think it is true that a graph with an Eulerian circuit must have an even degree for every vertex? Why might this be true? Does anyone have any ideas?
Do you pronounce the guy Euler?
Euler. Euler.
Euler.
Yep.
Okay.
Euler. Yeah. Someone typed in chat because you must use them only once. If you could expand on that, I'm not exactly sure what that means. Someone else typed in chat, if you have odd, you're gonna like go to the vertex again. Yeah, yes, that is on the right track. Because you have to have an even number so that you can come back. Interesting thought. Yeah, so thinking about what it means to have an even degree. Oh, we're also assuming it's simple and connected, by the way. So we're not going to deal with loops or anything like that. But yeah, so you can kind of think about your path. If you're going in an Eulerian circuit, you're going to start and end in the same place. And you're going to basically, you can think of it as go through all of the other points. And if you're going through a point, let's just say you had an odd degree for this vertex. Let's say you had 3 vertices, not vertices, edges coming out of this vertex. If you wanted to use all of these edges, because remember we're dealing with an Eulerian circuit, so we need to use every edge exactly once. I could use this edge. Let's change my color. I could use this edge and go here, and I could leave through another edge. And because I have to use every edge, I still have to use this edge somehow and come back. But then I'm kind of stuck here because there's no more edges. I can't reuse any of these other 2 that I've already used. I can't come back the same way I came because I can only use each edge exactly once. So I'm kind of stuck. I'm just ending right here. And since we assumed that we didn't start at this vertex, that also doesn't work. Even in the cases where you are starting at a certain vertex, let's say this is my starting and end point, because remember, we are dealing with the circuit, so as there is a start point and there is an end point, and those 2 points are the same point. So if I start at this vertex, let's say I have another let's say I had one edge coming out like this. I had another one coming out like this, another one coming out like this. If I started at this point, I would have to leave through one of these edges and go do other stuff, random stuff over here. And I would come back to this point eventually using this second edge. And I could also leave that point again through this third edge. but then I would have no way of coming back. And remember, this is our start and end point, so I still cannot complete my circuit like this and maintain the fact that we use each edge exactly once. So you can kind of think of it, another way to think of it as you have to, for every point in this graph, in your Eulerian circuit, you're going to have to enter the point, and you're also going to have to exit the point because you can't just stay there. And in order for you to both exit and enter it, you have to have an even degree. Every time you enter, you have to also exit because you don't want to just stall at that point. And that's why you need to have an even degree in order to have an Eulerian circuit. Someone noted in chat, actually you can have an Eulerian circuit with one of them with an odd degree, not the start and end. Do you want to unmute and elaborate on that? Did you find an Eulerian circuit with an odd degree? Oh, that's okay, yeah. So yeah, this is true. This theorem is true. This is a theorem. And yep, you have to have even degree. So it should not be possible to find an Eulerian circuit with odd degree. All right, so now we've talked about Eulerian circuits. What about Eulerian walks? So first of all, does someone want to tell us the difference between an Eulerian circuit and an Eulerian walk? Rose?
For an Eulerian walk, you don't have to go back to the spot you started with. Instead, you can just like end anywhere you want.
Yeah, exactly. Oh, continue.
But then for Eulerian circuit, you have to end where you started.
Yeah, exactly. Yep, Eulerian circuits are going to end at the same place it started. Eulerian walks don't necessarily have to do that. They can just they can start and end in different places. All right, so what do we think about the conditions, about the degrees for every vertex in Eulerian walks? Someone noted in chat, you can have an odd number for an Eulerian circuit. An odd number of what? Odd number of vertices, edges, degree? Yep, you can. You can have, I don't think there's any restriction on the number of vertices that you can have for a graph with an Eulerian circuit, but there is this limitation of an even degree for each vertex. So degree and number of vertices, both important concepts, but we are referring to the degrees in this theorem. All right, so what do we think about the limitations on the degrees for each vertex in a graph with an Eulerian walk? Do we think we can have points with odd degree if we have an Eulerian walk? All right, I think we will maybe do some examples and then come back to this problem. So
Wait, so is it like is it can you like walk all the bridges?
nope, you cannot, because remember in that graph there were vertices with odd degree, and we know that if you have an odd degree in your vertex, you cannot have an Eulerian circuit. So no, it is not possible to traverse all of those 7 bridges.
That's what I thought.
Sorry, could you repeat that? I didn't quite catch that.
That's what I thought.
Nice job then. Yeah. You might leave a bridge behind. Yeah, you will leave a bridge behind. Yeah.
Yeah, every time I tried, there was always like a bridge left.
Yep, that's what happens. Yeah. So it is not possible. Someone else said in chat, you stall, right? For Eulerian walk, for Eulerian path and odd degree. Not quite, it is. Oh, for Eulerian circuit. Yep, you'll eventually stall at some point because you'll either run out of like places you can go from you'll basically like have like quote unquote no way out of that point because you have already used up all of the edges. Yeah. All right, so a couple more terms. A path is different from a walk, which is a little confusing. A path is basically a walk that does not repeat vertices. So you cannot go to the same vertex twice. A Hamiltonian path is a path that passes each vertex in a graph exactly once. So not only does it not repeat vertices, it also visits every single vertex. A Hamiltonian cycle is a Hamiltonian path that starts and ends at the same vertex. Yeah, and it's important to note that they don't necessarily have to use up all of the edges in a graph. So we only care about each vertex being visited once. We do not care about the edges all being visited once. All right, so a quick review of this terminology. What is the difference between a path, a cycle, and a walk? Does someone want to raise their hand and recap for us? Or type in chat? Yeah, yep. So with Eulerian, it's edges. Hamiltonian, it's vertices. Yeah, Hamiltonian cycles, going to visit every vertex once and end up at the same place. Eulerian, oh yeah, it's important to note for Hamiltonian cycles, visits every vertex once, except for the place it starts at, which it will come back to, obviously. And then for Eulerian cycles, yep, it's going to be with edges. Visit every edge once. You can remember that Euler and edges both start with E. So Eulerian, we care about edges. And then Hamiltonians, I don't know, H and V can make it some mnemonic or something. Or just remember it's the other one. So what about the first question? Does anyone remember the difference between a path, a cycle, and a walk? Yeah, I see someone typed in chat, a cycle starts and ends at the same spot. Yep, cycle starts and ends at the same spot. The other two don't necessarily have to. What about the difference between a path and a walk? What was the distinction between those two? Yeah, I see someone typed in chat, a path cannot be at the same vertex. Yeah, paths can only visit each vertex once. Good. All right. What about this question? Can you have a Hamiltonian walk that is not a Hamiltonian path? Just an application of the definitions we introduced in the previous slide. A Hamiltonian walk that is not a Hamiltonian path. All of these terms are confusing. Yeah, a little bit. Yeah. Walk and path, they sound kind of similar, but they're different. So remember, a walk is just any kind of way of traversing along a graph. There's kind of not really many restrictions. A path has a restriction that it cannot visit a single vertex more than once. And remember, a Hamiltonian path is going to visit each vertex exactly once. What do we think about that? See, someone typed in chat, yes. Do you want to unmute and explain your reasoning? Or type in, oh, go ahead.
For a walk, you can visit vertices more than once. You don't have to do that. But for a path, you have to. And a walk, you can visit them as much as you want.
That's true. So thinking about this, if you had a Hamiltonian walk that is not a Hamiltonian path, that would mean that you would have a Hamiltonian walk that does visit a vertex multiple times. And the answer to this question is actually no. You cannot have a Hamiltonian walk that is not a Hamiltonian path, because if that occurred, that would mean that you have a Hamiltonian walk that visited a vertex more than once. But remember, that's not possible because a Hamiltonian walk must visit each vertex exactly once. So it can't visit it more than once or less than once. Someone asked, so a path can visit a vertex multiple times and a walk only once, or the other way around? Yeah, it's the other way around. So the path is the more restrictive one, and the walk is the less restrictive one. I guess one way you can kind of remember that is a walk just sounds more casual, like you're just strolling around going for a walk. And a path is like you have a very strict kind of way of going places. So it's the more restrictive one, aka the one that can only visit a vertex once. Does this make sense? Does anyone have any questions? Yes, I can repeat what a Hamiltonian walk. Hamiltonian walk, well, all Hamiltonian walks are going to be Hamiltonian paths, but Hamiltonian path is a path that passes each vertex exactly once. So it's like a Hamiltonian. Oh, so the answer to this question, remember the answer to this question was that you cannot have a Hamiltonian walk that is not a Hamiltonian path. So you can essentially think of a Hamiltonian walk and the path as the same thing because it's always going to be a path. And remember, something is Hamiltonian, it's going to pass each vertex on this graph exactly once. Any other questions? But you can't, someone said in chat, but you can't go to one vertex 2 times for the start and end on the cycle, but on the path you can. I'm not exactly sure what you mean by that, but I guess I'll say something slightly related, which is that for the Hamiltonian cycle, it is okay that you kind of leave the vertex that you start on and you kind of come back to it. That is okay. Yeah, you can kind of think of it as like the cycle might not even have like a specific start or end. So you can think of it, it just passes through that point exactly once. It's going to go into the point and go out of the point once each. So for this point is going into it, and then it's also going out of it, going into it, going out of it. And the same for the start point as well. If this was my start point, I'm going out of the point. I haven't gone into the point yet though. I'm going out of my start point, blah, 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 blah. And then at the end, I'm going back into it. So it's still going in, going out once. Yep. All right, so a little bit of practice. Now that we learned some stuff about Hamiltonian stuff, just a quick review of Eulerian walks and Eulerian circuits. Looking at these two graphs, do we think there exists an Eulerian walk for both of these two graphs? If you think there is, you can raise your hand and annotate. I'll call on you and you can annotate on this drawing to draw what you think the Eulerian walk is. David? Oh. Okay, never mind, I guess.
Wait, what's a Eulerian walk again?
An Eulerian walk is a walk that passes each edge exactly once. So it doesn't have to start or end on the same place, but it does have to pass each edge exactly once. David? You can go ahead and annotate. David. Oh, remember it has to be a continuous way. So could you label your start and end point? I'm not exactly sure what your walk was there.
I think it was this.
All right, I do see a valid Eulerian walk here. Yeah, nice. Okay, I'm gonna erase and redraw this. But yeah, let's say, I think David started right here. This was his start. Yeah, and if I go along like this, I guess I'll label my vertices so you know which one I traveled to. 2, 3 to 4. And then come back here. Remember, it doesn't matter that I'm visiting this vertex twice because we only care about the edges. And then go down here like this. Yes, an Eulerian walk does exist for this graph. Does an Eulerian circuit exist for this graph? Yeah, it does not exist. And why is that? Why does an Eulerian circuit not exist? Yep, because we are going to have odd degree. If we look at this top point or this bottom point, they both have degree of 3. So an Eulerian circuit does not exist. But this is interesting because we just showed that an Eulerian walk does exist. But there are two there are two vertices here of odd degree. So you can have vertices of odd degree in an Eulerian walk. Specifically, you can have the start point and the end point of your Eulerian walk have odd degree, but all of the other vertices still must have even degree. And that's because you're only going to quote unquote come out of the first point once. You're not going to like return to it again, like you don't necessarily have to. And the same with the end point. You can kind of stall at the end point, and that's okay too, because that's your end point. All right, so we're a little bit over time. I will leave you guys with that. To convince yourself of that, you can also attempt to draw an Eulerian walk on this graph that's starting on this point and ending on this point, because those two both have even degree. And I don't think you will be able to. But you can attempt and kind of convince yourself that way. Rose, did you have something to say?
That was up from before, sorry.
Okay, no problem. William?
For the second one, I think I figured it out, but I'm not sure.
Figured out whether it exists or what it is.
The Eulerian walk. Eulerian walk.
Awesome. Yeah, an Eulerian walk does exist. I don't think we have time for that right now. Someone asked, can you repeat what you just said? Yeah, so basically for an Eulerian walk, you can have vertices of odd degree, but the vertices of odd degree must be the start and end point. So yeah, the start and end point will have odd degree, and all the other points on the graph will have even degree for an Eulerian walk.
Bye.
All right. If you have any questions, you can say after class. Otherwise, I will see you guys all later. Thanks for coming. Bye.
Bye.